Okay, so for this little lecture, we'll focus on section 6.1, which focuses on normal distribution. Okay, so first we need to understand what a probability density curve is. Okay, the purpose of this curve is to describe the results in a population. But as I said in chapter 1, very rarely do we work with the actual population. So often we gather a sample and we're trying to generalize those findings to the population. Okay, so here we have a sample of 65 cars and we measured how much emission they create. Okay, we created different classes and each class has a width of 1. Okay, so you see this here and we have different frequencies. Here we're using the relative frequency. Okay, so the class that has the highest relative frequency is the class between 1 and 1.99. Okay, so this is with a sample of 65 cars. But let's imagine that we were not working with a sample here, but rather we would be working with the population. We would have a lot more data here, so this would allow us to make the class width even smaller. Okay, so let's imagine that this is the same data, but here we're working with the population. See how now instead of having a number of classes that have width of 10, we have many classes with smaller width. Okay, if we were to use this histogram, we could draw a curve, so a smooth curve, and this is a probability distribution. Okay, so this is what it looks like. Okay, so if we're looking at the probability distribution, we need to understand that there are 3 characteristics that describe the probability distribution. First of all, it can only be used with continuous variables, not discrete, not qualitative, obviously, because we're looking at histogram and not bar graph, so only continuous variable. Second characteristic, the area under the curve, if we are using relative frequency, equals to 1.0. Okay, and if we are converting the relative frequency into a percentage, the area under the probability curve will equal to 100%. Okay, so this will be crucial later on, and you will understand why. Okay, and finally, let's say that the area under the curve between two values A and B. Okay, so we're trying to look at a specific area under the curve. There are 2 meanings associated with a specific area between 2 values. The first meaning can be seen as a proportion. Okay, so the area under the curve between A and B could represent the proportions of people who scored between those 2 values. Okay, so that's one meaning. The second meaning has to do with probability. Okay, so basically, you could be interested in knowing the probability that someone would get a score between A and B. Okay, both of those concerns or both of those are focusing on a specific area under the curve, and we'll get to practice this in a sec. Okay, so now that we know the 3 characteristics of a probability distribution, let's look at an example here to help us understand. Okay, so here we have an example. We have the same probability distribution as we had before, and we are focusing on the area between 4 and 6. Okay, so I will ask you 4 questions, so try to answer the questions here, and I will actually give you the results in your next class. Okay, so my first question is, what proportion of the population is between 4 and 6? Okay, so looking at this graph here, this probability curve, try to answer this question. Second question, if a value is chosen at random from this population, what is the probability that it will be between 4 and 6? Okay, so what is the probability that a value would be between 4 and 6? Third question, what proportions of the population is not between 4 and 6? Okay, so we're looking for the proportion of the population which is not between 4 and 6. And finally, if a value is chosen at random from this population, what is the probability that it is not between 4 and 6? Okay, so we are looking at the probability that a value chosen would not be between 4 and 6. Okay? So make sure you write your answers down, and we will cover them. I will give you the results or the answers in class. Okay, so now we're moving to something a little bit different. So we're no longer looking at probability distribution, but we're looking at normal distribution. Okay, so we looked at this in the past, so we already know quite a bit about normal distribution. Okay, so we know that a normal distribution is something that is symmetrical. So what you will find on the right side is exactly what you will find on the left side. You also know that the mean, mode, and median are all the same, which is in the center of the distribution and represents the highest point of the curve. Okay? What we also need to understand is that a normal distribution is always symmetrical. Mean, median, and mode is always the same. However, the height of the peak could change. So this means that the variation of a curve, a normal distribution, could vary. Okay, so here we have a good example. We have two normal curves. Both of them have means of 0. This is a little symbol for mean. But one of the curve has a wider range and a wider degree of variation. So one curve has a standard deviation of 2, so the smaller one, and the other one has a standard deviation of 1. Okay? Another characteristics of normal distribution is that the mean doesn't always need to be the same. So here we have the shapes exactly the same, so the variation is the same in both curves. However, one has shift to the right compared to the other one, so they have two means that are different. Our first curve has a mean of 0, and the second one has a mean of 5, and both of them have standard deviation of 1. Okay? So now we understand this better. We've also learned, based on the empirical rule, that instead of using the actual score, so the score for the mean, we can represent a normal distribution based on number of standard deviation above or below a curve. Okay? So we know here, and we've learned this, that 68% of all our data is between -1 standard deviation, so 1 standard deviation below the mean, and 1 standard deviation above the mean. We know that 95% are between -2 standard deviation and +2. And we know that 99.7, which is almost all, of the population is between -3 standard deviation and +3 standard deviation. Okay, so those are all characteristics of a normal distribution. Okay, so the normal curve is really useful, and now we're kind of experts with it. Is really useful when your scores that you are interested in are a full number of standard deviation above or below. And then we can apply the empirical rule and say, okay, 68% of the scores are between this and this, or 95%. The problem becomes when the scores that you are interested in are in between two standard deviation. So they're not exactly 2, they're not exactly 1 above, but they are in between. If they are in between, we can no longer use the simple normal curve. We need to use a standard normal curve. Okay, what is a standard normal curve? A standard curve is a curve that has a mean of 0 and a standard deviation of 1. Okay, so basically this curve, this is the standard normal curve. Standard mean score of 0 and standard deviation of 1, which we don't see here. Okay, but how do we get this curve? So let's say we're going back to this example that I used last class. Let's say we're interested in hourly wage of Canadian, okay, and the population mean is $25 per hour, and the standard deviation is $5 per hour. So how can we, instead of using this data, how can we create a curve with a mean of 0 and a standard deviation of 1 that will represent the variable that we are interested in? The answer is by using z-score. And we've learned about z-score in the previous class. Okay, so let's just look. Let's make sense of all of this. Okay, so let's try to understand how a standard normal distribution has a mean of 0 and a standard deviation of 1. Okay, so remember the values that I just gave you. I said, let's imagine that we are looking at hourly wage that Canadians are making. And the mean score is actually $25 per hour. And this distribution for the population has a standard deviation of $5 per hour. Okay? How can we make this into a distribution with a mean of 0 and a standard deviation of 1? Well, let's go back to our z-score formula. So the formula that I have right here. Okay? Let's play with these values here. We want to convert the mean score that is here into a standard score, a z-score. Okay? So we have here our score is 25. So we compute 25 minus our population mean, which is 25, and we divide it by 5. If we do this math, 25 minus 25, we get 0 divided by 5. So for an individual score of 25, which happens to be the mean of my population, this equals to a z-score of 0. Okay, so that shows us how we can convert the mean into a z-score. Okay, what about one standard deviation? If we have a mean of 25 and we add one standard deviation to the score, we now have an individual score of 30. Let's convert this individual score into a z-score. Okay, so we take our individual score, which is 30, minus the population mean, okay, and then we try to divide this value into the standard deviation. 30 minus 25, we get 5 divided by 5, it gets 1. So all of a sudden, we have our population with a mean of 0 and a standard deviation of 1. Okay, so that's really what a standardized normal distribution is. It's just taking the actual scores, the raw data, and transforming them with the z-score. Okay, so this way, we're looking at the distribution here. All of a sudden, no more raw data. We have a mean score of 1, and then we have standard deviation of 1. And there you go. That's our standard normal distribution. Okay, so if we're looking at this here, now we know that we have standard normal distribution. Okay, why? Because we have a mean of 0 and a standard deviation of 1. Okay, so let's say I'm giving you a score, and on this distribution here, the z-score, because remember that the 0, 1, 2, and 3 are actual z-scores. Okay, so it's not raw data, it's a standard normal distribution, and in a standard normal distribution, at the bottom here we have z-score. Okay, so let's say we're looking at someone's score, and this person's score is 1.47 z-score. Okay, 1.47 z-score. And we want to know the area under the curve. So the proportions of people that did worse than this person. So that scored actually lower than 1.47 z-score. So how can we answer this question? Okay, what do we need to do? Well, first of all, we need to understand that the 1.47 represents a z-score. Really important, okay? Because we have a very useful tool when we're dealing with z-scores and standard normal distribution. Okay, so the very important tool that I just mentioned about is the table that you have in your textbook, table 8.2 at the end in appendix, okay? And it's called a cumulative normal distribution. Okay, look at the graph that we have at the top here. We have our standard normal distribution because we have a mean of 0 and a standard deviation of 1. Okay, what we first need to understand with this table, look at the first column here. Those are less z-score. Okay, so remember the example that I just gave you. We aren't interested in looking at a z-score of 1.47. Okay, so shortly we will be looking for that specific score. But before we do so, let's look again at the graph at the top. The values that we will get in the table will be the proportions of, or the probability to the left of that z-score. Look at this shaded area. So basically it will be the proportion or probability of getting a score less than that specific z-score, less than that standard score. Okay? So really important to understand this. So remember the score that we are looking for. We're looking for a score of 1.47. Okay, so 1.47, I come here, I have 1.4. Okay, and then I need to have 47. If I go back here, I'm looking at this column all the way here. Okay, so 1.47, I'm looking at this specific value right here. So with a z-score of 1.47, we have 92.92% of the scores that would be less than this. Okay, the area under the curve left of that z-score would be 92.92% or 0.9292. Okay? Okay, but what if what we really wanted was to know the proportions or probability of getting a score greater than a z-score of 1.47. Okay, so we're no longer interested to the left side, but we want the right side of 1.47. So how would we do this? Okay, so here's the table again. Remember that we have a z-score of 1.47, which represents 0.9292 to the left of this value. If we were interested in the other side of the curve, so getting a score, the area greater than 1.47, we would take 1, because the entire area under the curve is 1, minus the value that we have highlighted here, which is 0.9292. Okay, and that would give us the area to the right. Okay, so we would do 1 minus 0.9292, and we would get an area under the curve of 7.08% or 0.0708. Okay, so that's how we would do this. We could also use the table the opposite way, okay, not to identify the area under the curve, but to actually find a z-score. So the z-score that equals to a specific area. Okay, so let's look at this here. On this graph, I've actually identified an area that equals to 0.48. But I don't know exactly here what the value of the z-score would be. Okay, I want 0.48, and I need to find the actual z-score. Once again, I need a table to do this. Okay, so to answer the question of which z-score corresponds to an area of 0.48, I looked in the table and I tried to find the area that is as close to the area that I'm investigated about. And here I find 0.48, okay? This corresponds to a z-score of minus 0.0, and in order to find a decimal, I scroll up, okay? And that would, my answer would be a z-score of minus 0.05. So that would be my answer. So a z-score of minus 0.05 equals to an area under the curve of 0.48. Okay, so now that you know what a standard normal distribution is, how to use z-scores, how to use the normal distribution table, next class we'll start putting this all together, so we'll be playing with all kinds of different concepts. I will cover this in class, as I said, but I just wanted to give you an example or a problem to work with to see how far you can get. If you don't know what to do with this problem, don't worry about it. I will explain it in class, but if you can manage to do it without me, this will stick. Okay, so try to see how far you can get, and if you don't complete it, don't worry about it. I'll help you out next class. Okay, so focusing on the same example as I used previously, the distribution of hourly wage in Canada is normally distributed with a mean of $25 per hour and a standard deviation of 5. What is the probability that a Canadian makes less than $14 per hour? Okay, try to see what you would do with this problem. Okay, good luck, and I'll see you in class.